So I'm pretty sure I forgot to hit record at the beginning of this lesson yesterday. So let's just launch straight into it. Cohen, good morning. Let's keep going. So, yesterday, kinematics began. Kinematics is the study of motion, the how fast, the how far, the how long. Talking about scalars and vectors, these mathematical objects that these measurements can kind of get absorbed into. If the measurement has just a magnitude, if that's all we care about to define this object or this measurement, we call it a scalar. Things like mass. Your mass doesn't have a direction. Things like, I am 4 kilograms left. That doesn't make sense. Vector quantities have a magnitude and a direction. One of the things we're gonna toss something in here. I hope you have some space, because I forgot to do it yesterday in my excitement to get to position. I'm gonna toss something right in there. The thing I forgot is when we're talking about vector quantities with both a magnitude and a direction. When we're talking about directions. Good morning, Harshan. We set these things up. There's a few different ways you can set up directions. They all come from kind of the cardinal set of directions. We've got north, we've got south, we've got east, we've got west. We also have things like right, left, up and down. And typically we consider these things to be, some of them are positive, some of them are negative. Typically, which ones are which? Sorry? Yeah, typically up is positive, down is negative. And also typically, what else is true? Which other ones do we deal with here? Yeah, James. Yeah, right is typically positive, left is typically negative. Now, I mean, the universe is right-handed, and so this kind of makes sense. And when I say the universe is right-handed, that'll make more sense later. But these, just so we're aware here, what we call positive and negative is pretty arbitrary. I'll say is arbitrary. Now what I mean by that, if that word is not one that you're familiar with, is we just kind of assign it. So for any given problem, as long as you're internally consistent, it doesn't matter what you call positive or negative. You might say, you know what, for this particular question, down is actually going to work better to be what I'm going to call the positive direction, which makes up, down is positive, up is negative, right? So as long as you're internally consistent, typically this is how we arrange things. North and east, up and right are all positive. Left and down, west and south are all negative. But again, as long as you're internally consistent, it generally doesn't matter. So then we had position. Position is a vector because you have to measure your position from somewhere. And Manuel, I'm sorry, I forgot to look up whether or not Ecuador is truly 0, 0. Fine. Go so fast. I'm pulling up Google Maps and I'm going 0. 0, 0.
That's the way to do it.
0, 0. There it is. It is in the ocean.
You gotta put it HDMI. You gotta put it so we can see it.
I don't have to, but Connor, for you, I will.
You're the best.
Unless Ecuador is blue.
I can't see anything. Oh, there we go. That's like not really close to Ecuador.
That doesn't look very close to Ecuador at all, actually. Ecuador's over here.
Is Ecuador?
So 0-0, it's on the equator, as I said yesterday, which you agree with because the Ecuador goes through the equator. And I also said I'm pretty sure 0 goes through Greenwich, England. Oh, lucky there. Let's just zoom in. Yeah, Luis, that's what I'm trying to justify. Yeah. But now you're just trying to kill some time, Manuel. Unfortunately, where is Greenwich, England? Luis, you know where Greenwich is? I mean, obviously. I am not taking more than, I swear, I'm not going to take a lot of time to do this. Where is Greenwich? Either way, you wanted 0-0?
No.
There it is. Off the coast of, it wasn't Ghana.
I think there's a viewing marker there.
It was Ghana.
Oh, can you put it in like satellite?
Yeah, there it is. No, I'm not putting it in, okay, fine, I'll put it in satellite. Okay, so unfortunately, Manuel, it's not Ecuador. Ecuador is on the equator, that's cool. But yeah, no, there we go. Okay, back to this. So all of the positions, actually, and it's good that, Manuel, you brought it up. Every position on our planet is measured from that location. Like, it looks like it's 400 kilometers off the coast of Ghana, and what looks like maybe 1,000 kilometers off the coast of Gabon. That is 0-0. One of them being the equator, one of them being the meridian that punches through Greenwich, like where the day begins on our planet. And that is, so all the positions are measured from that place. Everything relative to some origin, there it is. You saw our global origin. Yes, Connor?
La mitad del mundo says the middle of the world is Ecuador, so
Says the middle of the world is in Ecuador?
yeah.
Where did you look?
The circle is Ecuador the middle of the world. Or the center of the world.
No.
I've been there. Like, water moves down. Like, there's a line. There's a line straight through the resort, and on the left side, there's like a bucket of water. And if you unplug it, the water goes like in one direction. On the other side, you unplug it, it goes in the opposite direction.
That's not a thing. It's not a thing.
That's a thing.
I have a video for you. I have a video for you. Is it the same bucket on both sides of the equator?
No, they're on opposite sides.
Oh, okay. So that has everything to do with the structure of the bucket. I can unplug a bucket here and make it drain the opposite way you're expecting it to drain. I have a video for you. Have you heard of the Smarter Everyday guys?
I want to be smarter every day.
Okay, so there's two YouTube channels. We're gonna kill some time here. 2 YouTube channels. One is Veritasum and one is Smarter Everyday. These are 2 different YouTubers that tackle concepts like this. And one of them went down to Australia and the other one was in California. And they did the exact same on the opposite sides of the equator, and they flushed the toilets or they drained the tub. They spun the exact same direction. And it has everything to do with the structure of the thing that's draining. Where you are correct to suggest there's something called the Coriolis effect, and that affects wind currents, it affects ocean currents, but it's on a global scale. Unless the water is like perfectly still, you're never going to notice it. Because you're right, the spin is different. And that resort might sit on the equator, but it's not 0-0, Manuel. It might be 0-90. Cool, it might be a quarter of the way around from 0-0. But then every quarter could say exactly the same thing. The next quarter is probably going to be in the Pacific. The one on Ecuador might be the only 0-90 that's actually on land. That might be true, which would be cool. But 0-0, as it's defined, longitude, latitude, is in the middle of the Atlantic, well, not the middle, but it's on the right-hand side of the Atlantic Ocean off the coast of Africa. I'm sorry. I'm sorry. Do you have heritage in Ecuador?
Yes.
Have I destroyed it entirely?
We're just gonna
not describing.
Okay, well, maybe work on describing some words and come back to me when you have them. So we've got position. Position is a vector. It's where you are relative to some origin. We use D with this little arrow above it to represent the fact that this is a vector. Distance is a scalar. We don't care which direction the distance implies. The distance is always add. And in this case, this distance is the orange line here. How far something is away, or the actual ground you cover to get there. And then displacement is the straight line distance from where you start to where you've ended. And this is the blue line. This is where we kind of ended it here. It's this guy. When I say the straight line, I should actually have gone like that. There it is there. So in this case, distance is 20 meters. The distance is always add. And I'll write it right down here. The displacement in this previous example, I think, Luis, we ended the class with you telling us all that the displacement there was 12 meters.
Yeah.
So you may have walked 20 meters, but you have only been displaced 12 meters. Because when we talk about your displacement, we don't care about the path you took. All we care about is where you started and where you ended. So all that matters is where you started and where you end. Anyone want to take a stab at whether or not displacement is a scalar or a vector? I think it's a scalar. Why do you think it's a scalar? Do we not? If I care about where you end, if I just say you've been displaced 12 meters, this person could be anywhere in the circle. Looks something like that. Is that a useful piece of information?
Yes. I agree with that.
I'm sorry to say you're wrong. It's not useful, because if you tell me, okay, well, I've been displaced 12 meters, that's great. That doesn't help me find where you're at. Maybe let's define displacement yet another way. And maybe this will help you. The other way that we define displacement, so Connor, you were getting hung up yesterday on the fact that displacement is also another word we use for you get in the bath and the water goes up. Or maybe you've heard the story of Archimedes and the king in ancient Greece, and the king comes to Archimedes and says, "My crown's made of gold. I need you to prove whether or not my crown's made of gold." And so Archimedes, he's trying to figure out how to figure out if the crown's gold, and he's sitting in the bath, and he's like, this is the classic eureka moment. Apparently, that's when he shouted eureka and sprinted out of the bathtub naked to find the king to prove what the crown was made of, because he used the density. It's the density of pure gold. You can put it in the bathtub, and depending on how the water gets displaced, blah blah blah. And so that's the idea you have for the concept of displacement. Khalil, good morning. But that is not the only definition for something like displacement. In physics, we define displacement to be a measure of the change in position. Where were you before? Where are you now? And how have you been displaced? Because position is a vector and displacement is a change in position, displacement is also a vector. Does anyone want to guess? Maybe you've seen the symbolism for it before. Does anyone want to guess how we define a change in position using symbolic notation here, displacement? Connor.
Well, if you start somewhere, and you can determine a change when you're
No, I'm sorry. What I'm asking you is, can you give me something like this? Position was D with an arrow. Distance was just D. No vector symbol. Is there something that you can give me to represent the change in a position as a variable? There's a Greek letter that represents change in. Have you seen it before?
The delta symbol.
The delta. What's the delta look like?
Triangle.
Where did you learn about delta?
Science.
Perfect.
Physics. Or not physics.
You've taken physics before?
No, like science 10, just the physics.
Nice. With the energy.
Yeah.
Okay. So delta is that Greek letter there. And if it's a change in a position, we say that this is delta D with an arrow above it. This represents a change in a position. And this is going to be equal to something. There's a mathematical, or there's an algebraic expression for this. A change in a position. How do you find the change in something? Subtract what, Manuel? In what order? Current's where you are now.
You want to start with where you were and then subtract where you are now.
Does that make sense?
No.
Because then you get a negative number.
So Zaid, how should we do it?
You do the, like, if you had 50 and then you displace it up to 60, you do 60 minus 50.
Correct. So then the displacement is
10.
10. So a change in a position is delta D, and mathematically it's going to look like your final position minus your initial position. And that's going to give us our displacement, delta D.
And what's the after 9?
Final minus initial. And if to make matters even more confusing, sometimes often what we end up doing is this delta D is actually just going to become D with an arrow above it, and we understand that the symbolization for position and displacement are exactly the same, and the only one we care about is displacement, which, to make our lives even better. So for example, let's do some examples. We'll do a couple here. If I've got a person here, there's Manuel. Manuel is currently at his desk. He walks, 6 meters that way. Turns around, walks 6 meters back. The distance he traveled is what? 12 meters, you betcha. His displacement is what? Why?
His overall position never changed.
Because
The 6 meters there.
his overall position never changed. So his displacement is 0. Cool. What if I have this? Manuel again. Because it doesn't actually have to be Manuel, but you know what? It can be. 6 meters out, 3 meters back. Distance traveled is what? 9. Cool. What's his displacement? Almost. 3 what? 3 meters. But displacement is a vector, so we need a direction. 3 meters which way? He was here. This is where he ended. And he grew, apparently. Where did he end relative? Which direction did he end at relative to where he started? Yeah, from what you're seeing and what's on my paper, how we're all going to draw this, is his displacement is 3 meters, and that arrow is pointing to the right. So we have to include that in our quoting of displacement. Displacement is 3 meters right. Let's do one more. Mine is going to be a little bit small. I don't have a ton of space there at the bottom. We have our stick person. Our stick person goes, let's see, 4 meters this way. And then goes 3 meters this way. What's the distance? Thank you. 7 meters. What's the displacement? Right and up are a right angle to each other. They're 90 degrees to each other. So Luis already said it back there. All we care about is the straight line distance from where you started to where you ended. So this is what matters to us. If that's a right angle, that's a hypotenuse then. I picked my numbers nicely so that we can do this relatively easily. This here is 5 meters. Well, how'd you do that? You did the Pythagorean theorem. 4 squared plus 3 squared square rooted is 5. So our displacement then is
north of east.
how far north of east? No, it's 5 meters, but how far north is he from east?
Oh, east, north 3, east. Oh, sorry. Yeah, north 3, east 4 meters.
Okay, so there's a few ways that we can quote this. You could say that this 5 meters is where he actually is relative to where he started. This 5 meters, some direction we haven't determined yet, could be considered 4 meters east plus 3 meters north. That's one way that we could say where he's gone. Or this is a triangle, right? What other information can we pull off a triangle? We can find the angle. That angle right there. What angle is that? How are you going to find that angle? This is why we reviewed trig a week ago. So it's going to be tan inverse of opposite over adjacent is equal to, what's tan inverse of 3 over 4? Grab a calculator, Manuel. Yeah, James. Do we know that for sure? I don't know if that's a 30. No, that's not a 30, 60, 90 triangle. That's 1, 2, root 3. I think it's 36 and a bit. 36.86? 869, so 36.87, if I round that properly. Okay. So then the other way we could say this thing, just like I did in my door example over here, is we could say that this person is 5 meters, that's straight line distance, 36.87 degrees north of east. Because I started at east and I went up. That's the other way that you can quote these vectors. Now, the vast majority of what we do in this course is not going to make you do things like that off at weird angles. A lot of that's going to get introduced in Physics 12, assuming you take Physics 12. But comments, questions, concerns on any part of this. There's a lot on there. We cool? Math isn't super scary, is it? Okay, Manuel, question.
Is kinematics like the shortest unit?
It'll probably be the longest. Because it lays the groundwork for everything else. Because everything is just movement. Electricity, movement of electrons. Magnetism, well, believe it or not, movement of charged particles. Energy, movement, heat. Well, it's just a measurement of the movement of individual particles within a solid body. Everything comes back to how things move. And so kinematics is the basis for everything we have to study. Yeah, Luis?
I think the chemistry have it to like for intermolecular connections. You need to know the displacement of the molecule.
Yeah, no, you're right. Okay, so some examples here. What is the distance from car A to car B? How'd you do it? You very quickly, you threw that out there.
I added the distance from 0 to magnitude.
Okay, so you noticed, you looked very quickly and you said, well, that's actually 0. So here our car is over at -2, and then our car ends over here at 7. You just did that very quickly, and I appreciate that. So, distance here, 9 meters. Love it. Or that's actually measured in kilometers, 9 kilometers. Well, you didn't read all the question then, just like I almost didn't. The distance from car B to car A is also, sorry? It is also 9 kilometers. What's the position of car A? Car A is this guy here. What's the position of that car? -2 kilometers. Or what's the other way that you could quote that position? That's one way to do it. Absolutely, that would be totally correct. In this case, what is giving us the direction? That's not what's giving us the direction. Well, what? So in our answer, in this thing here, this -2 kilometers, which part of -2 kilometers is direction? Negative. The negative. In this case, it tells us that it's 2 kilometers to the left because we assume left to be negative. The other way you could quote this is if I said 2 kilometers and I didn't say 2 was negative. The other way I could quote this is 2 kilometers which way? Left. It doesn't matter which of these two you use. You could say -2 kilometers or 2 kilometers left. The one thing you don't want to do is say -2 kilometers left, because what would that mean? It means it's to the right, because what is negative left? Negative left is to the right. So one of these is how you'd quote your answer. How about car B? What's the position car B? 7 kilometers. But this is a little ambiguous here because we haven't specifically put in a plus sign. So I'm not totally convinced you know what the direction is. So we have to include some other piece of information. There's two ways, sorry? You could put to the right. What's the other way that you could explicitly put your answer in here? Yeah, you could just say the position of the car is positive or plus 7 kilometers. Either one of those would be totally acceptable. How about the displacement of car A measured from car B? How far are car A and B how far is car A displaced from car B? 9 kilometers left. Cool. Who said that? The other way you could quote that is -9 kilometers. I'm not going to write that in there, but just so you understand. And then the displacement of car B measured from car A. Nine kilometers, right. We cool with what's going on here? Okay. Next example, we've already kind of done this one. I decided I'm thirsty for a Slurpee. I'm going to go to a walk to the nearest 7-Eleven. We have one just down the road. In order to get there, I follow the sidewalks because safety is cool. Also, it's going to give me some nice angles. We're not jaywalking all over the place here. What is the distance I travel to 7-Eleven? 450 meters. How'd you do that? You add the numbers together. I went this way, and then I went this way. My distance is 450 meters. My displacement doesn't care about the path that I took. What's my how would I find my displacement? Same way. All I care about is the straight line distance from where I started to where I ended. So that's a 90. So I'm going to use Pythagoras again. I'll write it out in more detail this time. A squared plus b squared equals c squared. The side I'm looking for is represented by which letter in this relationship? C. So this is going to be 300 squared plus 150 squared equals c squared. So c equals the square root of 300 squared plus 150 squared. What's c? 335.4. We need units, meters. Cool. Is that a sufficient quoting of our displacement? No, because that would actually just give us a big circle, 335.4 meters around. We also need the direction. What is the direction of my displacement? Sorry? South of west. Or is it west of south? Which is which? West of south means I started at south and I went west. That would give me that angle in there. But how much west of south? That is the question that I'm posing to you. Well, not you specifically, but all of you. How would I find out that angle given this triangle? Maybe it's a Friday morning in first block and we're all quiet, we're all tired. But James. Sorry, James? Tan inverse of opposite over adjacent. So it's going to give me 150 over 300. So that angle equals what? Sorry, 46? Oh, 26.57 degrees. So then the way we quote this, my displacement from Abby to 7-Eleven is 335.4 meters, 26.57 degrees, and Manuel already gave us the direction west of south. Comments, questions, concerns? Yes, Manuel. South of west means I start at west and I go down. That would give me this angle right here. If I go south from west, this is south of west. This one here is west of south.
Okay, so the second one is a wave set.
Yeah. It's quoted as the direction from where you began. Flip the page. I wanted to determine the position of the swimmer at the following times. This thing right here is a position time graph. We like graphs. Graphs are great. Position time graphs allow us to read the position of whatever we're graphing right off the graph. So at time equals 4 seconds, what is the position of the swimmer? Here we are at 4 meters. Looking up there. It's at 4 seconds, where are we? 8 meters. 8 meters east, cool. At 6 seconds, 6 meters east. Thank you, Tristan. At 10 seconds, Careful. Is it negative 2 meters or is it 2 meters west? Both are acceptable, but which one do you want? You can't combine them. You could say 2 meters west, or you could quote this thing as negative 2 meters. You can't do both. 12 seconds. Negative 4 meters. Okay. Now we're combining negatives and both. That's fine. 20 seconds, where are we at? Our swimmers turn around and now they're at 8 meters again. 8 meters is not enough. East, sure. Or I could just say positive 8 meters. I could have put a plus sign there. That would have worked as well. To find displacement, we've said it before, we'll say it again. Displacement is a change in your position. So it's your final position minus your initial position so to find the change in position from 6 seconds to 10 seconds, 60 was at 6 meters east, 10 seconds he's at 2 meters west. So to do the math here, our change in our position is going to be what? So there's a voice coming from the front corner here. Do you have a thought, Manuel? Sorry? I can't quite hear you, man. Negative 8. How'd you do that? So 2 meters west. So, but west doesn't really work here in the equation. So when we convert it, so what value are we going to use here? Negative 2. And we're going to subtract our initial position. Our initial position was? Yeah, positive 6 meters. Cool. So we're at negative, our displacement is negative 8 meters. Cool. How about 12 seconds to 18 seconds? Our change in our position, or yeah, displacement is change in position. What is the change in our position from 12 seconds to 18 seconds? What's our final position at the 18-second mark? Yeah, it's right here at 4. And that 4 is positive or negative? Okay, so we're at 4 meters, finally. And where did we start at the 12-second mark? We started at negative 4 meters. So what's our displacement from 12 seconds to 18 seconds? 8 meters, and it's strictly positive. Or we could say it was 8 meters which way? East. And the first one we can go back and say this was 8 meters which way? West. Cool. Comments, questions, concerns so far? Love it. Flip the page. Flip slowly. I'll flip slowly. You flip faster. Okay? So there's one more question with that same example. What is the swimmer's final displacement at the end of the swim? 0. 2 of you said it. Why? Because he started and stopped at the same position. If your position, your final position is equal to your initial position, your displacement is 0. I don't care how long it took you to get to no displacement. What's the total distance traveled by the swimmer? Sorry? Not 50 meters. Total distance. Total, the distance traveled is what? Naya, you have some thoughts.
I don't know. Well, he starts at 10 and all goes down to -4 meters.
Okay, so what's that distance? 10 to -4 is?
10 to -4.
Going from from a position of 10 meters to a position of -4 meters is what distance? Sorry? 14. And then he turns around and goes back to 10. So the distance is 14 plus 14, which is 28 meters. Displacement is 0. Distance traveled is 28 meters. 14 meters out, 14 meters back. Okay, so this is going to connect to concepts of velocity and speed. Velocity and speed are two different ways of describing how fast something's traveling. Speed is equal to your distance, the length of the path you traveled, divided by time. How long it took you to travel that path. Speed, is it we already said it. Speed is a scalar or a vector? It's a scalar. And speed is a scalar because distance is a scalar, and so is time. If the thing you're looking at is made up of scalars, it also must then be a scalar. So if it's a scalar, what does it not have? There's no direction. Velocity, we've already said, is a vector. So, and it's related to speed. What do you think the equation is for velocity? No. No. Speed was distance over time. What is our concept that looks a lot like distance, but is just, the vectorized version of it? I'm working on doing that right now. It's displacement over time. Thank you. So speed is distance over time. Velocity is defined as displacement over time. If it's displacement over time, velocity then must be a vector, which we've already said, but this is now why, because it's based on a quantity that is also a vector, which means it has a direction. Yes, Manuel. Oh, no, that was, sorry. I thought you were putting your hand in the air. That was Mrs. Dunn. I don't think she saw you. Okay, some examples. So a person travels for 1 hour and travels 90 kilometers. What's their speed? What's their displacement? So their speed is 90 kilometers divided by the time, which is 1 hour. So that's going to give us our 90 kilometers per hour. Actually, let's do it all. What's the velocity then? How would we say that? Well, you'd say it like 90 kilometers per hour west. Is how you'd end up quoting that. So in this case, speed and velocity are very similar. The only difference is the addition of west. The distance traveled is, you already pulled that out. The distance is 90 kilometers. The displacement is 90 kilometers, and then Manuel, you added west. So in some circumstances, your distance and displacement are exactly the same, and so your speed and velocity are then exactly the same. The only difference is we've added a vector or a direction here now. The where things get, and this is why things like speed and velocity, we don't quibble over these words. They mean the same thing, which is not true. I just put air quotes around it if you weren't looking at me. But this is often why we just quote them as the exact same thing. If a runner travels around a 400-meter track twice, returning to their starting position in 5 minutes, let's find their speed and their velocity. Sorry? Yes, I am recording. Yes, no, I made sure I was doing that at the beginning. So, a runner travels around a 400-meter track twice, returning to their starting position. So let's draw it. There's our runner. They went a 400-meter track twice. So speed is distance over time What's the distance they've traveled? They did it twice. It's 800 meters. And what's the length of time? Okay, it's in minutes. So their speed now is going to be what? What's 800 divided by 5? 160. And the units are meters per minute. Okay, so what about the velocity? Velocity is displacement over time. What's the displacement? 0. Took them 5 minutes to displace nothing. So the velocity is 0 meters per minute. And when it's 0, that direction doesn't make sense. Velocity is 0. Speed was 160 meters per minute.
How about if you do half that? So you did it twice, no, you only did it once and then did it half.
Okay, so then what would his displacement be if he went half?
Well, we would need to know what it is down, we couldn't just go around.
So if he ends up down here, we would need to know what this is.
Well, it takes 400 meters to go around once, it'd be 200 meters. No, because you need the straight down, not a curved around.
You don't need the curve, you want the straight line.
How do you figure that out?
We can't. Without knowing the shape of the track, we have no way of doing it.
Is it, wait,
We need the shape of the track to do the math.
is it not like a unique shape of a track?
I don't know what the standard shape of a track is. This is not specified. We don't know that this is an Olympic standard track.
Is that a thing?
One more question before Manuel derails us. A person travels north for 500 meters, then south for 30 meters. If this takes 240 seconds, what's the speed? What's the velocity? So the person went this way, 50 meters, turned around, went this way, 30 meters. Oops, sorry. I want the speed. Speed is distance over time. What's the distance traveled? 80 meters. Took them 240 seconds to do that. 80 over 240. That's 8 over 24. 0.3, repeating, meters per second. Okay, that's cool. How about velocity? Velocity is displacement over time. Now this person was displaced. That's where they started. This is where they ended. This is 20 meters. So the displacement now is going to be 20 meters divided by 240 seconds. So what's my velocity? .083 what? North. Thank you, Naya. And Naya, you need to get out of here.
Okay, I have like 10 minutes, 5 minutes.
Okay, I'm not sure classes. I don't think class is going to last 5 more minutes.
It's not 10:30.
Is it 10:30? Oh, there it is. Okay, so here's what you're doing. Flip the page. This is your homework. I want you to do these 5 questions over the weekend.
I will. What day do you want to do this?
Okay, ladies and gentlemen, this is your homework. I want you to do this. We'll take it up on Monday. Have a great day, guys. We'll see you later.